Let's begin by imagining a scenario you're probably all too familiar with. It's 2 a.m. The clock is glowing beside your bed. You're tossing, turning, staring at the ceiling, maybe scrolling through your phone. You know you've got to get up in 4 hours, but your brain just won't shut off. Morning comes and you drag yourself out of bed, hoping to push through the day on coffee and willpower. But what if I told you that just one night of bad sleep, not chronic insomnia, not sleep apnea, but just a single night of insufficient or disrupted sleep could set off a cascade of biological consequences? What if that one night affects your blood sugar, your immune system, your cardiovascular system, your brain, even your mood? Sleep is not a passive state of rest. It is an active, dynamic process, essential for life itself. During those hours of rest, your brain conducts deep cleaning, your hormones rebalance, your immune system resets, and your metabolism recalibrates. One night of bad sleep doesn't just make you groggy. It actually alters how your body operates at a cellular level. Let's start with glucose metabolism. After just one night of poor sleep, studies show a significant drop in insulin sensitivity. That means your cells are less responsive to insulin, the hormone that helps shuttle glucose out of your bloodstream and into your tissues. So what happens? Blood sugar levels rise. You may feel hungrier than usual, you may crave sugar and carbs, and your risk of developing insulin resistance temporarily spikes. In fact, in healthy young adults, one night of only 4 hours of sleep can reduce insulin sensitivity by up to 25%. That's equivalent to the level seen in early diabetes. Your body enters a pre-diabetic state after just one night. Now let's talk about immune function. Sleep is the time when your immune system does its heavy lifting. Natural killer cells, those frontline defenders that destroy virus-infected and cancerous cells, are reduced in activity by as much as 70% after one night of sleep deprivation. That means you're more susceptible to infections, viruses, and inflammation. It also means that even if you got a vaccine recently, your body might not respond as well. Research shows that people who sleep poorly the night before a vaccination produce significantly fewer antibodies, meaning weaker protection. Moving on to the cardiovascular system. One night of bad sleep increases sympathetic nervous system activity, your body's stress response. Heart rate goes up, blood pressure goes up. The next day, the body is more inflamed. C-reactive protein, a marker of systemic inflammation, is elevated. This is not an abstract concern. The day after daylight saving time, when millions of people lose just 1 hour of sleep, there's a documented 24% spike in heart attacks. Conversely, when we gain an hour, there's a 21% drop. That's how sensitive the cardiovascular system is to even a small disruption in sleep. And what about the brain? One night of bad sleep impairs cognition, memory consolidation, decision-making, and emotional regulation. You're more reactive. You're less focused. You're more prone to impulsivity and mood swings. Brain imaging studies show that the amygdala, the area responsible for fear and aggression, becomes hyperactive. At the same time, communication with the prefrontal cortex, the rational decision-making part of the brain, weakens. You're not just tired, you're actually neurologically impaired. On top of that, the glymphatic system, which is the brain's waste clearance mechanism, becomes active primarily during deep sleep. It's during these hours that beta amyloid, the toxic protein associated with Alzheimer's disease, gets flushed out. One night of fragmented or insufficient sleep, that flushing process gets disrupted. The result, elevated beta amyloid levels in the cerebrospinal fluid the next morning. Bad sleep also affects hormones, particularly cortisol, leptin, and ghrelin. Cortisol, your stress hormone, rises the next day, keeping your body or a flight mode. Leptin, which signals satiety, goes down. Ghrelin, which signals hunger, goes up. This is why you tend to overeat the day after poor sleep, particularly junk food. Your brain is seeking quick energy to make up for the lack of rest, and it pushes you toward the least healthy options. Now let's not forget the mood implications. Poor sleep is directly linked to increased rates of anxiety and depression. It's not just correlation. When sleep suffers, emotional regulation deteriorates. Irritability rises. Emotional resilience falls. You're more likely to experience negative emotions and less likely to feel pleasure. In fact, sleep deprivation has even been used in lab settings to induce depressive symptoms in otherwise healthy individuals. Even your gut microbiome is affected. One night of poor sleep alters the composition of your gut bacteria, shifting the balance towards species associated with inflammation, obesity, and poor metabolic health. That change happens fast, and it contributes to the systemic effects we've just discussed. All of this from just a single night of bad sleep. And this is important. Your body does not fully recover with one good night of sleep afterward. Some of the changes, like insulin resistance and increased inflammation, may linger for several days. This is why consistent, high-quality sleep matters so much. It's not about making up for a bad night on the weekend. It's about rhythm, regularity, and respecting the biology of rest. Your body is designed to function in sync with the sleep-wake cycle. When you disrupt that cycle, even briefly, the consequences are swift and profound. One night of bad sleep is not harmless. It's not just being tired. It's a temporary breakdown of multiple critical systems that you depend on every day. One night of poor sleep causes immediate insulin resistance and blood sugar dysregulation. This effect is not something that takes weeks or months to develop. It can begin in less than 24 hours. When the body is deprived of adequate sleep, particularly deep and REM stages, it triggers a series of hormonal and metabolic disturbances that impair glucose regulation. The pancreas may still release insulin, but the cells throughout the body, particularly in the muscles, liver, and fat, become less responsive to it. This means that glucose stays in the bloodstream longer, leading to higher blood sugar levels, which is a hallmark of insulin resistance. In studies involving healthy adults, even a single night of sleep restricted to 4 or 5 hours resulted in measurable drops in insulin sensitivity the very next day. These changes mirror the early stages of type 2 diabetes. In fact, after one night of insufficient sleep, some participants in controlled studies displayed blood sugar profiles similar to those with diagnosed prediabetes. This metabolic dysfunction is largely driven by an increase in sympathetic nervous system activity and the release of stress hormones like cortisol. When you don't sleep well, cortisol levels are elevated the next morning, particularly upon waking. Cortisol naturally helps mobilize energy by increasing glucose availability in the blood. However, when cortisol is high while insulin sensitivity is low, this creates a metabolic storm where it's released but cannot be efficiently cleared. This is why poor sleep often leads to fatigue, irritability, and a craving for fast energy, typically in the form of high carbohydrate or high sugar foods. The brain is compensating for a lack of rest by demanding a quick fuel source, and this only worsens the cycle of blood sugar spikes and crashes. Leptin and ghrelin, two hormones that regulate appetite, are also disrupted by even one night of poor sleep. Leptin, which signals fullness to the brain, drops. Ghrelin, which signals hunger, rises. The result is an increase in perceived hunger, especially for calorie-dense foods. People who sleep poorly not only experience more hunger the next day, but also tend to eat more throughout the day, especially late at night, which further impacts glucose metabolism. This behavioral shift reinforces the underlying biological dysregulation, making it harder for insulin to keep blood sugar under control. On a cellular level, sleep is a time when the body conducts critical metabolic housekeeping. Mitochondrial efficiency improves, cellular stress is reduced, and metabolic flexibility is restored. When this process is interrupted, mitochondria become less efficient at processing glucose and fatty acids, which leads to an accumulation of metabolic waste and a drop in cellular energy production. Over time, this inefficiency contributes to inflammation, oxidative stress, and the development of insulin resistance at the tissue level. But even acutely, just from one poor night, this process is initiated, and blood markers of metabolic stress can be measured within hours. There's also an effect on the liver, which plays a central role in regulating glucose levels. During sleep, especially deep sleep, the liver reduces its output of glucose into the bloodstream through a process called gluconeogenesis. When sleep is disrupted, this suppression is lifted, and the liver begins releasing more glucose than needed, further increasing blood sugar levels. This unregulated hepatic glucose output compounds the effects of insulin resistance and leads to higher fasting glucose readings the following morning. In fact, people who sleep fewer than 6 hours per night are significantly more likely to show elevated fasting glucose and hemoglobin A1C levels, even when controlled for diet and physical activity. Additionally, poor sleep affects the hypothalamic pituitary adrenal HPA axis, which governs many hormonal systems, including those involved in energy balance and glucose control. The HPA axis becomes more reactive and less stable following inadequate sleep, leading to more pronounced cortisol surges, especially in the early morning hours. This heightened cortisol response exacerbates insulin resistance and alters the circadian rhythm of glucose metabolism, which normally helps regulate how well the body handles carbohydrates during different times of the day. Disruption of this rhythm makes the body more insulin resistant. Even at times it would typically be more tolerant to glucose intake, such as in the morning. Poor sleep also alters muscle insulin sensitivity, making it harder for skeletal muscle, the largest glucose sink in the body, to absorb sugar from the blood. This is especially concerning because muscle glucose uptake is a primary way the body maintains stable blood sugar. Reduced muscle uptake results in post-meal glucose spikes, which further strain the pancreas to produce more insulin. Over time, this can contribute to pancreatic beta cell exhaustion, but acutely it leads to inefficient glucose clearance and increased oxidative stress in muscle tissue. Immune system function drops significantly, increasing susceptibility to infections. Just one night of insufficient sleep can dramatically suppress the activity of key immune cells, leaving the body more vulnerable to viruses, bacteria, and other pathogens. One of the most well-documented effects is the decrease in natural killer NK cell activity. NK cells play a crucial role in the early defense against viral infections and in the detection and destruction of cells that may become cancerous. When sleep is disrupted or shortened, NK cell activity drops by up to 70% in the following 24-hour period. This decline compromises the body's first line of immune defense, which is responsible for identifying and eliminating infected or abnormal cells before they can multiply or spread. In addition to NK cells, sleep also regulates cytokines, which are small proteins that facilitate communication between immune cells. Some cytokines promote inflammation to help the body respond to infection or injury, while others suppress inflammation to promote healing. When sleep is restricted, the balance of pro-inflammatory and anti-inflammatory cytokines is disrupted. Levels of inflammatory cytokines such as interleukin-6 IL-6 and tumor necrosis factor alpha TNF increase even in the absence of infection. These elevated cytokines can lead to systemic inflammation, fatigue, and a heightened risk of chronic diseases, but they also impair the body's ability to mount an effective immune response when needed. Sleep loss also alters the function of T cells, which are critical for adaptive immunity. T cells are responsible for identifying specific pathogens and coordinating targeted immune responses. During deep sleep, T cells adhere more effectively to infected cells and destroy them efficiently. However, after one night of poor sleep, studies have shown that the adhesion molecules on the surface of T cells are downregulated. This makes it harder for T cells to interact with their targets, reducing the precision and effectiveness of the immune response. Furthermore, the number of circulating helper T cells, which are essential for orchestrating the immune response, also declines after acute sleep deprivation. Sleep plays a vital role in the production and release of immune-supporting substances such as melatonin. Melatonin is more than just a hormone that regulates sleep-wake cycles. It also functions as an antioxidant and has immune-modulating effects. When sleep is compromised, melatonin levels decrease, and its protective influence on the immune system is reduced. This leaves immune cells more susceptible to oxidative stress and less capable of defending the body against external threats. The timing and quality of sleep are also crucial for the proper functioning of the lymphatic system and lymphoid tissues, which house and transport immune cells throughout the body. Poor sleep disrupts lymph circulation and can impair the movement of immune cells to sites of infection or inflammation. Moreover, the spleen and bone marrow, key organs in the immune system, show altered activity after even brief periods of sleep loss, resulting in reduced output of white blood cells and impaired immune surveillance. Another key point is how poor sleep affects the body's response to vaccination. In clinical trials, individuals who had a poor night of sleep before or after receiving a vaccine showed a significantly blunted antibody response. Their immune systems produced fewer neutralizing antibodies, meaning their bodies were less prepared to defend against the targeted virus. This has been observed in vaccines for influenza, hepatitis, and even more recently, COVID-19. The reduction in antibody titers after sleep loss is so significant that sleep is now considered a modifiable factor that can impact vaccine efficacy. Sleep also plays a regulatory role in fever response, which is one of the body's natural defense mechanisms during infection. When sleep is disrupted, the body's ability to mount a proper fever is impaired, and the coordination between immune signals that trigger this response becomes less efficient. This can delay the immune system's reaction to pathogens and allow infections to take hold more easily. Even the gut-associated immune system, which comprises nearly 70% of the body's immune cells, is affected by a single night of bad sleep. The intestinal barrier becomes more permeable, allowing bacteria and toxins to leak into the bloodstream, a condition known as endotoxemia. This not only burdens the immune system with additional threats, but also provokes an exaggerated inflammatory response, which can interfere with proper immune signaling. Sleep loss also affects the bone marrow's capacity to produce hematopoietic stem cells, which are the precursors to all immune cells in the body. After a night of poor sleep, the production rate of these vital stem cells declines, potentially leading to longer-term immune suppression if poor sleep becomes habitual. The immune system is intricately tied to the circadian rhythm, and when that rhythm is disrupted even briefly, immune gene expression shifts out of phase, further impairing cellular function and coordination between immune components. Cardiovascular stress rises with elevated blood pressure, heart rate, and inflammation after just one night of poor sleep. The cardiovascular system is highly sensitive to sleep quality and duration because it relies on rest periods during the night to reset and regulate key functions such as blood pressure control, vascular tone, and heart rate variability. When sleep is disrupted or shortened, the body's autonomic nervous system becomes imbalanced, with a significant tilt toward sympathetic overdrive. This means the stress response becomes dominant, activating the fight or flight pathway even in the absence of immediate threats. As a result, adrenaline and norepinephrine levels rise, leading to vasoconstriction and increased heart rate, which in turn elevates blood pressure. This physiological state, which is meant to be temporary in times of danger, becomes sustained in the absence of adequate sleep, placing unnecessary stress on the heart and blood vessels. In addition to the sympathetic nervous system activation, there is a parallel suppression of parasympathetic activity, which is the body's relaxation and recovery system. The vagus nerve, which helps slow the heart rate and promote calmness, becomes less active. Heart rate variability, a marker of cardiovascular resilience and autonomic balance, drops significantly after one poor night of sleep, indicating that the body is under greater strain and has reduced capacity to adapt to stressors. Low heart rate variability has been associated with increased risk of cardiovascular events, including heart attacks and sudden cardiac death. Sleep also regulates the endothelial function of blood vessels. The endothelium is the inner lining of the blood vessels, and it plays a key role in regulating vascular tone, inflammation, and clotting. After just one night of insufficient sleep, endothelial function declines. The blood vessels become stiffer and less able to dilate, which contributes to increased vascular resistance and higher blood pressure. This endothelial dysfunction is one of the earliest markers of atherosclerosis and is strongly predictive of future cardiovascular disease. In clinical studies, flow-mediated dilation, a standard test of endothelial function, is significantly impaired after acute sleep deprivation. The inflammatory response also plays a major role in cardiovascular stress after sleep loss. Inflammatory markers such as C-reactive protein, CRP interleukin 6, and tumor necrosis factor alpha TNF all increase in the bloodstream following just one night of poor or fragmented sleep. These inflammatory cytokines promote oxidative stress within the vascular system, damaging blood vessel walls and promoting the development of plaque. Chronic elevation of these markers is associated with increased risk of heart disease, stroke, and hypertension, but even short-term spikes can lead to acute cardiovascular events, especially in individuals with pre-existing risk factors. One of the most dramatic examples of how sleep affects the cardiovascular system is seen in the transition to daylight saving time, when people lose just 1 hour of sleep. Studies show a 44% increase in heart attacks the day after this shift. Conversely, in the fall, when an hour of sleep is gained, there's a 21% drop in heart attacks. This illustrates just how acutely sensitive the cardiovascular system is to sleep loss even in healthy individuals. The same trend has been observed with strokes, arrhythmias, and episodes of sudden cardiac death, all of which show increased incidence following even brief periods of sleep deprivation. Poor sleep also disrupts the natural nighttime dip in blood pressure known as nocturnal dipping. Normally, blood pressure falls by 10 to 20% during sleep, allowing the heart and vascular system to rest and repair. When sleep is interrupted or shortened, this dip is either blunted or absent altogether. Non-dipping status has been strongly associated with increased cardiovascular risk, including a greater likelihood of left ventricular hypertrophy, heart failure, and kidney disease. After just one night of inadequate sleep, blood pressure can remain elevated throughout the following day and into the next night, sustaining the cycle of cardiovascular strain. Sleep also influences the body's ability to regulate cholesterol and lipid metabolism. After a night of disrupted sleep, levels of triglycerides and LDL cholesterol tend to rise, while HDL cholesterol, the protective form, may drop. These changes are not just chronic phenomena, they occur acutely and have been measured within hours of sleep loss. This lipid imbalance contributes to the buildup of plaque within the arteries and further impairs endothelial function, setting the stage for atherosclerotic disease progression. Clotting factors also change with poor sleep. Platelets become more adhesive and aggregation increases, meaning that blood clots are more likely to form. This hypercoagulable state increases the risk of thrombosis, which can lead to heart attacks and strokes. Even the fibrinolytic system, which breaks down clots, becomes less efficient after one night of insufficient rest, tipping the balance toward clot formation rather than dissolution. The net result is a heightened cardiovascular risk profile that begins to form almost immediately after a single poor night's sleep. Brain function declines with impaired memory, focus, emotional control, and detoxification after just one night of poor sleep. The brain is uniquely dependent on quality sleep for cognitive restoration, synaptic pruning, and the removal of neurotoxic waste. When sleep is cut short or fragmented, these critical processes are interrupted, leading to noticeable impairments in thinking, reaction time, learning, and mood. One of the most immediate effects of sleep loss is a reduction in working memory, the brain's ability to temporarily hold and manipulate information. This function, centered in the prefrontal cortex, becomes less efficient, resulting in difficulty concentrating, poor decision-making, and a higher likelihood of making mistakes even in simple tasks. These impairments are not subtle. They've been shown to be comparable to those seen with alcohol intoxication when sleep is restricted to just 4 or 5 hours. Sleep is also vital for long-term memory consolidation, a process that transforms new information into lasting neural representations. During deep sleep, especially slow-wave sleep and REM sleep, the brain replays and strengthens memories from the day. This includes not only factual knowledge but also procedural memories such as how to ride a bike or play a musical instrument. Without adequate sleep, especially REM sleep, the hippocampus, a brain structure critical for memory formation, struggles to encode new information. Studies using brain imaging have shown that the hippocampus becomes disconnected from the neocortex after just one night of poor sleep, meaning new memories are less likely to be stored effectively. Students pulling all-nighters before exams, for example, often retain less than if they had studied less and slept more. Cognitive flexibility and creative thinking are also compromised after sleep loss. The brain's ability to make connections between disparate pieces of information, which is essential for problem solving and innovation, is reduced. Tasks that require divergent thinking and insight become more difficult. The prefrontal cortex, which supports logical reasoning and planning, becomes less active, while more primitive brain regions such as the amygdala become hyperactive. This imbalance contributes not only to poor decision-making but also to increased emotional reactivity. Emotional regulation is one of the most sensitive domains impacted by inadequate sleep. After just one night of poor sleep, the threshold for frustration, irritability, and anxiety becomes significantly lower. Brain scans reveal that the amygdala, which processes emotions like fear and anger, becomes overactive in response to even minor stressors. At the same time, the connection between the amygdala and the prefrontal cortex, the part of the brain responsible for executive control and emotional regulation, is weakened. This disconnection makes it more difficult to control emotional responses, which is why people often feel more emotionally volatile and less resilient after a sleepless night. The brain's stress response is amplified, making situations feel more overwhelming than they would with adequate rest. Mood disorders such as depression and anxiety are strongly linked to poor sleep, and even one night of sleep deprivation can trigger symptoms in vulnerable individuals. Sleep affects the balance of neurotransmitters, including serotonin, dopamine, and norepinephrine, all of which play essential roles in mood regulation. When sleep is insufficient, these neurotransmitter systems are disrupted, leading to an imbalance that can manifest as low mood, apathy, and reduced motivation. In individuals with underlying mental health conditions, even a single night of poor sleep can worsen symptoms and interfere with treatment responses. On a cellular level, the brain engages in a unique form of housekeeping during sleep through the glymphatic system. This system clears out metabolic waste products that accumulate during waking hours, including beta, amyloid, and tau proteins, which are strongly implicated in the development of Alzheimer's disease. The glymphatic system becomes highly active during deep sleep, when cerebrospinal fluid washes through brain tissue, removing toxins and debris. When sleep is interrupted or shortened, this cleansing process is significantly impaired, leading to the accumulation of harmful proteins and oxidative stress within neural tissues. Imaging studies have shown increased levels of beta amyloid in the brains of people who experience just one night of sleep deprivation, suggesting that even brief disruptions can accelerate neurodegenerative processes. Sleep also supports neuroplasticity, the brain's ability to adapt, form new connections, and reorganize itself in response to experience. This adaptability is essential for learning, recovery from injury, and maintaining cognitive performance across the lifespan. After a poor night's sleep, the brain's plasticity is reduced and its ability to learn new information or adapt to changing circumstances is diminished. This decline in flexibility contributes to the feeling of mental sluggishness and difficulty adapting to new tasks or environments. Even creativity, which relies on the brain's ability to form novel associations, is significantly impaired after sleep loss. Tasks that require insight or abstract reasoning become more challenging, and people report a decreased sense of mental clarity and inventiveness. These effects compound over time if sleep disruption becomes chronic, but they begin after just a single night without adequate rest. Hormonal imbalances trigger increased hunger, cravings, and stress reactivity after just one night of poor sleep. Sleep plays a critical role in maintaining hormonal balance throughout the body, and disruption to this balance can begin within hours of inadequate rest. Among the most noticeable changes is the alteration in appetite-regulating hormones, particularly leptin and ghrelin. Leptin, a hormone produced by fat cells, signals to the brain that the body has enough energy stores and creates a sense of fullness. Ghrelin, produced in the stomach, does the opposite. It signals hunger and stimulates appetite. After a night of poor sleep, leptin levels drop while ghrelin levels rise, creating a powerful physiological urge to eat more, even when energy needs have already been met. This imbalance doesn't just increase appetite, it also shifts food preferences. People are more likely to crave high-calorie, high-carbohydrate foods such as sweets, breads, and processed snacks. Functional MRI studies have shown that after sleep deprivation, the reward centers of the brain become more active in response to images of junk food, while activity in the regions responsible for decision-making and impulse control decreases. This makes individuals more likely to overeat and less able to resist unhealthy choices. Even in tightly controlled clinical environments, subjects consistently consume more calories, particularly from fat and sugar, after one night of insufficient sleep compared to when they are well rested. The dysregulation of hunger hormones is compounded by changes in insulin sensitivity. When the body becomes temporarily insulin resistant after sleep loss, glucose doesn't enter the cells efficiently, leading to elevated blood sugar and an energy deficit at the cellular level. This perceived shortage of fuel prompts the brain to seek more food, especially fast-digesting carbohydrates that can provide a rapid energy boost. The result is a vicious cycle where poor sleep leads to increased hunger, which leads to overeating, which then further disrupts metabolic balance. Beyond hunger hormones, poor sleep also has a profound impact on the hypothalamic pituitary adrenal axis, or HPA axis, which governs the stress response. Cortisol, the primary stress hormone, typically follows a natural daily rhythm, peaking in the early morning and declining throughout the day. However, after a night of bad sleep, this rhythm becomes distorted. Cortisol levels are elevated upon waking and remain abnormally high throughout the day. This prolonged elevation puts the body in a state of chronic stress, even in the absence of an external threat. High cortisol not only contributes to increased blood pressure and blood sugar, but also further stimulates appetite and promotes fat storage, particularly in the abdominal region. Increased cortisol also affects mood and emotional regulation, contributing to feelings of anxiety, irritability, and restlessness. These psychological effects make it even harder to make thoughtful food choices or engage in calming behaviors that could support recovery. Instead, the body is primed for survival mode, seeking out quick energy and emotional comfort through food and impulsive behaviors. Over time, this hormonal pattern can contribute to weight gain, insulin resistance, and even the early onset of metabolic syndrome. Sleep deprivation also disrupts the balance of sex hormones, including testosterone and estrogen. Testosterone, which is vital for muscle maintenance, mood stability, and metabolic health in both men and women, drops significantly after sleep restriction. Studies show that just one night of 4 or 5 hours of sleep can reduce testosterone levels by 10 to 15% the next day. This drop in testosterone can lead to decreased physical performance, reduced motivation, and lower energy levels, which makes it harder to engage in physical activity and further worsens metabolic outcomes. In women, poor sleep can affect levels of estrogen and progesterone, which play essential roles in regulating appetite, mood, and reproductive health. Disrupted sleep can lead to menstrual irregularities and may intensify symptoms of premenstrual syndrome. In both sexes, poor sleep also reduces levels of growth hormone, which is crucial for tissue repair, fat metabolism, and muscle regeneration. Growth hormone is primarily released during the early stages of deep sleep, and when sleep is cut short, this process is severely limited. The result is a reduction in the body's ability to repair and recover from daily wear and tear, including exercise and minor injuries. Melatonin, the hormone that regulates the sleep-wake cycle, is also compromised when sleep is delayed or interrupted. While melatonin itself is not a direct appetite regulator, it influences the timing and release of other hormones throughout the night. Poor sleep patterns can delay melatonin production, disrupt circadian rhythms, and alter the body's internal clock, leading to further misalignment of hormonal release and metabolic processes. This misalignment increases the likelihood of late-night eating and abnormal feeding schedules, both of which are linked to poor blood sugar control and weight gain. All of these hormonal changes begin to take shape quickly after a single night of disrupted sleep and compound in severity when poor sleep becomes a habit. Gut microbiome shifts toward pro-inflammatory, obesity-linked bacterial strains after just one night of poor sleep. The gut is home to trillions of microorganisms that play a central role in digestion, metabolism, immune function, and even brain health. This complex ecosystem is highly sensitive to lifestyle factors, particularly sleep. When sleep is disrupted, even for a single night, it alters the composition and activity of the gut microbiota, tipping the balance from beneficial bacteria and towards species associated with inflammation, insulin resistance, and weight gain. These changes are not theoretical. They have been observed in both human and animal studies using fecal samples to analyze microbial populations before and after sleep restriction. One of the first changes observed for poor sleep is a decrease in microbial diversity. A healthy gut microbiome is characterized by a wide range of bacterial species that contribute to metabolic flexibility and immune resilience. Reduced diversity is a hallmark of gut dysbiosis. Staying away from processed foods. A state in the gut becomes dominated by a narrower set of bacteria, many of which are less beneficial or outright harmful. Sleep deprivation reduces the abundance of bacteria such as Lactillus and Bifidobacterium, which are known for their anti-inflammatory properties and support for gut barrier integrity. At the same time, it increases species like Firmicutes, certain strains of Clostridium and Protobacteria, which are often found in individuals with obesity and metabolic syndrome. These pro-inflammatory bacterial strains produce endotoxins such as lipopolysaccharides, LPST, which can damage the lining of the gut and make it more permeable, a condition known as leaky gut. When the gut barrier is compromised, LPS and other bacterial products can leak into the bloodstream and trigger systemic inflammation. This state of endotoxiemia has been linked to a wide range of chronic diseases, including type 2 diabetes, cardiovascular disease, and autoimmune conditions. After just one night of insufficient sleep, markers of intestinal permeability begin to rise, and blood levels of LPS increase, indicating that the protective barrier of the gut is already beginning to break down. Sleep loss also affects the timing and rhythm of digestion itself. The gut operates on a circadian rhythm just like the brain and other organs. There are clocks within the cells lining the gastrointestinal tract that regulate when digestive enzymes are released, when the gut moves food along through peristalsis, and when nutrients are absorbed most efficiently. Disruption of sleep alters these rhythms, leading to a mismatch between when food is consumed and when the body is best prepared to digest it. This can lead to impaired nutrient absorption, changes in bile acid metabolism, and increased fat storage, especially when late-night eating is combined with poor sleep. Poor sleep is also known to influence short-chain fatty acid production in the gut. Short-chain fatty acids like butyrate, acetate, and propionate are byproducts of fiber fermentation by gut bacteria and play a crucial role in maintaining gut health. Butyrate, in particular, helps nourish colon cells, reduce inflammation, and reinforce the gut lining. After a night of sleep deprivation, levels of these short-chain fatty acids can drop, which weakens the gut barrier and reduces the anti-inflammatory tone of the intestinal environment. Staying away from processed food. This shift not only increases vulnerability to gut-related disorders, but impairs metabolic regulation throughout the body. Another effect of sleep deprivation on the microbiome is the increase in bacteria that are more efficient at extracting calories from food. Certain strains are better at harvesting energy from complex carbohydrates, and their dominance in the gut has been associated with increased caloric absorption and fat deposition. In studies where individuals were subject to sleep restriction, these calorie-harvesting bacteria increased in relative abundance, which may partially explain the link between poor sleep and weight gain. Even when calorie intake is controlled, sleep-deprived individuals tend to gain more fat compared to those who are well-rested, suggesting that microbial changes are influencing energy balance at a fundamental level. The microbiome also communicates directly with the brain through the gut-brain axis, a bidirectional network that uses the vagus nerve immune signaling and microbial metabolites to send messages between the gut and the central nervous system. After sleep loss, disruptions in the microbiome have been shown to influence mood, stress response, and cognitive function. This is partly due to changes in the production of neurotransmitters such as serotonin and GABA, both of which are modulated by gut bacteria. When sleep is compromised, the microbial production of these neuroactive compounds is altered, leading to heightened anxiety, lower stress tolerance, and impaired emotional regulation. These effects are compounded by changes in eating behavior that often follow a poor night's sleep. Individuals tend to consume more processed foods and fewer fiber-rich fruits and vegetables, which further depletes the beneficial gut bacteria and reinforces dysbiosis. This creates a feedback loop in which sleep loss damages the microbiome, and a damaged microbiome contributes to further sleep disturbances through increased inflammation and altered neurochemical signaling. This loop begins quickly, and while the full impact of changes becomes more significant over time, the microbiome begins to shift measurably after just a single disrupted night of sleep.